Okay, so I think I posted this on Canvas. I've got midterm 2 topics, and so this is what we have here. Okay, so Wednesday, May 11th, right here in class, pen and paper. So kind of like midterm 1, just and you get a sheet of notes, and you can have stuff written on the front and back. I'll send out a seating chart, and I'm looking at 4 to 5 problems total. Again, it's always a little bit of a trying to figure out how long, what the appropriate length is for a thing. Okay, so these are possible questions. One is the numeric gradient for a neural network. So I'll draw a very simple neural network with like one hidden layer and maybe like 2 nodes in the input layer, 2 nodes in the hidden layer, and 1 node or whatever in the output layer or something. Okay, something simple. And then as far as activation functions go, we'll keep it simple. Either the identity function, basically you don't do anything to it, or maybe the ReLU function, which basically is the identity if it's positive, and then it's just 0 if it's negative. Okay. Loss function will just be kind of our squared error loss, so maybe the mean squared error, or the sum of squared error, or 1/2 of whatever it is, And then I'll give you like a very, very small set of data, maybe like 2 observations. And then I'll also provide kind of your initial weight and bias matrices. And then you'll calculate the gradient for one of these matrices numerically, right? So if it's like so if there's a weight matrix, then to calculate the gradient, you have to add, you perturb each value. You add like a small value, and in the homework you added like 10 to the negative 4, 0.0001 or something, and you saw what effect it had on the loss function, and you measured that. For the exam, we'll use like a much bigger value of epsilon, maybe like 0.1 or something, and we'll see what effect does that have on the loss function. So there's kind of basically you do forward propagation, and you see, and then you have to calculate the loss function, right? Forward propagation to get your new y hats, and then you calculate the loss function between your y and your y hats. Okay, does that kind of make sense? What's happening there? So I know you did the numeric gradient in the homework, but you basically wrote a loop and things like that. So make sure you can kind of do something similar by hand for the exam, okay? And the key here is, let's say you have 3 elements. You have to do each one of those elements one at a time, right? You don't just add 0.1 to all 3 elements at the same time. Okay, another problem, analytic gradient instead, okay? And again, simple neural network. And to keep things simple here, the activation function will just be the identity function, okay? So no sigmoid function, nothing else. Just keep that simple there, which makes the f prime is basically 1, okay? Loss function will be mean or sum of squared error, and again, small set of input data, maybe 2 observations, and I'll provide initial set of weight and bias matrices, and you'll calculate the gradient in one of these matrices analytically. Just so you're not like trying to do a whole bunch of back propagation during the exam itself, I would recommend that you review your homework and your notes and just write out what the, like if you have basically a neural network with 1 hidden layer, these the analytic gradients are pretty much going to be the same, right? It's just maybe the dimensions change a little bit, and so maybe in your notes that you're allowed to have, you probably want to put that in there. Okay, just so you're not. I mean, I won't stop you from doing back propagation during the exam, but I imagine that took a while on your homework and you don't want to be doing that during your exam. Okay. All right. Is that okay? Number 2, any questions there? Number 3, MLE, and we'll have a probability distribution with basically one unknown parameter. So I'll provide some kind of, I'll specify some probability distribution. It'll be a univariate probability distribution. And I'll provide either the PDF or PMF depending on whether it's continuous or discrete. One of these parameters will be unknown and you have to estimate it using the data. So for example, I could give you a normal distribution where maybe the standard deviation is, we'll pretend that it's a constant value or something, okay, and the mean is unknown and you have to estimate the mean. I mean, that's super easy for the normal, so maybe I won't do that, but okay, and then or the binomial distribution where n is constant but p is unknown or something, right? I'll provide some kind of probability distribution. Maybe what are some other ones? Poisson distribution. Poisson only has one parameter, the rate parameter, and things, right? And I'll specify. Like, I don't expect you to have every single PDF memorized, so I'll make sure the PDF's written out with what these parameters symbolize and stuff. Okay, and then I'll provide a sequence of observations, and then you'll do a maximum likelihood estimation. Okay, based on the observed data. Okay. And then you'll also calculate the Fisher information. And the definition of the Fisher information will be the negative expected value of the second derivative of the log likelihood. So, okay, so for maximum likelihood estimation, you'll have to figure out your likelihood function, and then you maximize it by, taking the derivative, setting it equal to 0, and solving. Okay, or you take the log of the likelihood, take the derivative of the log likelihood, you set that equal to 0, and you solve. And then for the Fisher information, you've basically already done half the work for the maximum likelihood estimation. You have the log likelihood and you've taken the derivative of it already. So for Fisher information, you'll just take the second derivative of that thing, second derivative of the log likelihood, and then you'll find the expected value. Maybe you guys can make some practice problems for each other. For number 3. Okay, I've got maybe a Bayes classifier using a Bernoulli or binomial distribution. Okay, and so the data will be a mixture of Bernoulli or binomial observations drawn from different possible classes. That's pretty much what one of the examples in the lecture was this. So the different bags of marbles. Okay, each bag of marble is basically a binomial observation, and they're drawn from different possible classes, right? They came from factory A or factory B or factory C. All right, so something similar. Each class has a different probability of success. Each factory has a different probability of success. The training data, this will be summarized for you, and that you'll get, how many observations from each class and the estimates of P, or the proportion for each class. And then I'll give you some kind of test case or test cases. And you say, based on the test case and the Bayes classifier, we're estimating it is, class A with probability 0.8 or class B with probability point whatever, okay? And that will be that. Is that okay? All right, or we could do a Bayes classifier and it'll be the normal distribution. This, again, to kind of keep things simple enough for you to do okay on the exam within the allotted time. Maybe it'll be like the univariate Gaussian, okay? Univariate Gaussian with some mean and some standard deviation, 1 over square root, 2 pi sigma, et cetera, e to the negative, whatever squared, okay? Again, I'll tell you, this is how many classes we have, and here are the estimates of the mean and standard deviation for each of these classes. I'll give you the formula for the normal PDF, and then, here's a new observation, okay? So for example, we could say class 1 has mean 10 and standard deviation 3, and class 2 has mean 15 and standard deviation 4, all right? And a new observation comes in with the value 12. Okay, what's the probability it's class 1 versus class 2 or something like that? That is pretty much what this problem will look like, okay? All right, and then a handful of conceptual questions. Conceptual questions will cover from lecture 3-2, which was our first lecture on neural networks, up to lecture 6-3, which is today's lecture, and that covers KNearest Neighbors classifier. Okay. We good? All right. Okay. So this document has been posted to Canvas, and all right. And let's take a look at today's lecture. Week 6 Friday. Here we go. All right, so we've looked at we're looking at classifiers, and the classifiers we saw earlier this week, we had the Bayes classifier, and then we made the naive Bayes, looked at the naive Bayes classifier, which is pretty much the same thing, except the naive Bayes classifiers, you're not estimating covariances, and we said that's useful when you have a bunch of things, and we said like for document classification, you can use the naive Bayes classifier. Okay, let's do KNearest Neighbors. KNearest Neighbors is another classifier. It's okay as far as classifiers go. I think it's kind of like a good starting point, but probably you don't really use KNearest Neighbors in too many production settings, just because it's very computationally intensive. Okay, but anyway, KNearest Neighbors, you have training data, right? And with a classifier, your training data is already all labeled, and that's why we're using it for training. So it says, okay, these observations are class A, and these observations are class B, and these observations are class C, or something like that, right? You got the iris data set, and you got your 3 species, or whatever other data set you have. And the way it works is you get a new test case. A new observation is has these values, and from there you measure the distance from the test case to every single other point in the training data. Now, what this means is basically KNearest Neighbors really only works if your variables are numeric. Okay? Now, technically, you could use categorical variables in a KNearest Neighbors classifier, but it is hard because you have to come up with distances between different categories. Okay? So it might be okay if the categorical variable is ordinal. Sure, you can kind of come up with some distances, but again, you have like the distances need to be comparable to each other, okay? And maybe you have to standardize these or something, right? So for example, you could have shirt size, small, medium, large, extra large, and you can say medium and large are closer to each other than medium versus extra large, okay? And that's a reasonable thing to say, okay? But if it's something like hair color, or maybe not hair color, let's say vehicle color, right? I don't know. Okay, well, actually, as far as cars go, there's only like what, black and silver and white cars, maybe a blue car and maybe a red car, and then some other colored car, right? Like as far as what colors you see. So how do you what's the distance between red car and black car, or what's the distance between blue car and white car? I don't know, okay? And for that reason, it's difficult to use K-nearest neighbors for when you have categorical variables, okay? Numeric variables, it works just fine. You're measuring someone's weight, you can say, okay, the distance from 150 pounds to 180 pounds is 30, okay? That's fine, okay? That's an easy thing, okay? So anyway, you measure the distance from your test case to all of the other observations, okay? Usually we use Euclidean distance. You can use other distance metrics. So you can have the Manhattan distance, or I don't know, what other distances you want, okay? Once you calculate the distance to every single other training point, and by the way, this is the reason, this step number 1 is the reason why we don't like K-nearest neighbors, is because if your training data has 1 million observations, you have to calculate 1 million distances. And that can be very expensive in terms of how much computational power you have to use, right? So that could take a while. You then sort the resulting distances, and then you take the K observations with the smallest distances. And then looking at those top K observations, the nearest neighbors, that is your K nearest neighbors, the ones with the smallest distances, you are going to, each one of those observations gets a vote as far as what the class should be, and the class with the highest representation is the one that gets selected for our class estimate, okay? Let's see. And the examples I'm going to show you today, they're all two-dimensional. And so when you look at it, you're like, why do you bother calculating the distance to every single other point? Because visually, we can easily see visually in 2 dimensions which points are close and which points are far away, okay? But if your data exists in 17 dimensions, figuring out which ones are your nearest neighbors is a lot harder to do, okay? So that's a lot harder if you have high dimensional data. So all of the examples for illustration are 2-dimensional, and it feels silly that we're going to be calculating the distance to every single other point. But the truth is most of your data in high dimensions, it's not as easy to visualize, and so you do end up having to calculate the distance to every single other training data point. A big issue is, what K do you use? Okay, do you use the 1 nearest neighbor, the 2, 3, 4, 5, 10th nearest neighbor? How many nearest neighbors do you have? And your choice of K will influence the performance of the model. Smaller values of K tend to lead to overfitting, and they're more influenced by whatever is in their local neighborhood, whereas larger values of K will generally smooth out these boundary zones, and it may not be smooth, but you'll end up having kind of the opposite problem of overfitting, or we might call this underfitting, or we end up having kind of this, low variance, high bias type of situation, okay? And you can use cross-validation to estimate the performance of the model for different values of K, in that if you have your training data, you randomly select some to be some kind of holdout set, and you say, all right, let's test our prediction performance for the holdout set for different values of K, and so maybe you have 1,000 observations total, you put 100 in your holdout set, and you say, okay, if I use K equal to 1, how many times do I get my holdout set wrong, right? And maybe you make 20 mistakes, all right? And then you have K equal to 3, you say, how many mistakes do I make in my holdout set? Okay, and then maybe you make 15 errors or something, right? And so you can adjust the K and figure out kind of your classification errors on the holdout set for different values of K. And that could help you pick what value of K to use. Again, there's not always an easy answer. A lot of times you'll see there's kind of your classic L thing, where initially super small values of k, you make more errors, and then as you increase your k, the number of errors you make decreases, and then as you increase your k to be too big, maybe your errors start climbing back up. Sometimes you end up in situations with ties as far as which class should a observation belong to, and there's no set strategy for resolving ties, and you can kind of pick some of these things. So in general, if you only have two classes and you pick an odd number for your neighbors, then you'll never have to worry about ties. Okay? But as soon as you have more than two classes, like 3 classes, you can end up with ties. Okay? Well, yeah, if you have two, if you even, or if you have k even, right? If you say k equals 10 and there's 2 classes, you could end up in a situation where you have 5 and 5, right? So generally we say, okay, pick k odd, k equals 9, right? And then you don't end up getting into this tie situation. But if you have, let's say, 3 classes, you could have k equal to 9, and you could end up with a 4-4-1 split, okay? And then you have a tie, or a 3-3-3 split, and you have a tie, okay? So what do, right? So there's a few ways to deal with this. One is you just say unclassified. We don't, right? One is you switch to the one nearest neighbor, and you say, okay, and if you do one nearest neighbor, there's never going to be a tie. You can select randomly among the top tied groups. So if A is 4, B is 4, and C is 1 with 9 nearest neighbors, then you can just randomly flip a coin between A and B. It's probably not the best method there, but it's valid, okay? Or you could, among the top tied groups, so if A and B have 4 and C has 1, then you can select the group with the closest neighbor. So between A and B, which one has the closest neighbor? And you might say, okay, class B has the one neighbor that's closest, okay? And that's not necessarily the same as the one nearest neighbor, because it could be that class C, and which has 1, a vote of 1, ends up the closest neighbor, but there's no one else in C that's nearby. So those are ways to resolve ties. Okay, let me give you your first view quiz answer, which is the letter A. The letter A, as in apple, is your first view quiz answer. Okay, all right. The rest is just a bunch of pictures of showing KNearest Neighbors. KNearest Neighbors is a simple algorithm, and I've intentionally left off the code because that's your homework assignment, okay? Where you code up the KNearest Neighbors algorithm. Okay. All right, so here I'm generating some training data, and I'm using the multivariate normal in 2 dimensions. We're going to have 14 in class A and 10 from class B, and this is what my data look like, okay? So I've got, I forget, I think class A is blue, class B is red, and we want to say, all right, if I pick an observation somewhere, should it be red or should it be blue? Okay, so here we're going to put a dot right here. Okay, what do you guys think, red or blue? Well, I intentionally picked, I think, an ambiguous spot where you're not quite sure if it should be red or blue. Okay, so here's our test case, 0, -1. So what we're going to do is we measure the distance from this dot to every single other observation, okay? Now, again, in 2 dimensions, you can say, oh, these ones are the closest here. Why are you bothering measuring the distance here? Again, in 2 dimensions, we can easily see that. But imagine this data being in 17 dimensions, okay? Now it's a lot harder, right? Now you have to like plot all of these things in 17 dimensions, and I don't even know how to do that. Right? Because at best we can see in 3 dimensions. So I don't know. You 17 dimensions, and you have to like have some rotation of the data and some hyperspace or something. Okay. So anyway, if you have k equals 1, this is the one nearest neighbor, and I've tried to illustrate this by drawing a circle with this radius. And you can say, okay, there's nothing closer. it's red. So the one nearest neighbor is red, so this point will be classified as red. Okay. If k equals 3, this is the third nearest neighbor. All right, so we have 3 neighbors in this circle. And so we have 2 red versus 1 blue, so this is going to get voted as red. If you have k equal to 5, these are the 5 nearest neighbors. And we see here there are 3 that are blue and 2 that are red. And so this observation would get classified as blue. And with k equal to 7, this observation is just barely closer than this one. It's like they're very close, but this one is just a touch closer. But it doesn't matter because you have 4 blue and 3 red, and so k equal to 7 gets voted blue. Okay. Is that all right? Okay. Okay, what about this observation? What is this going to get classified as? Red. This one feels a little bit more like it should be red. Like it's on the red side, right? Okay, so again, measure the distances to every other point. K equal to 1, here's the nearest neighbor, it's red. K equal to 3, these are the 3 nearest neighbors. It's still, we got 2 to 1, still red. K equal to 5, okay? 3 red, 2 blue, it's still red. K equal to 7, it's still 4 red, 3 blue, so 4 red is still going to be red. And if we, you know, if you keep it going, I think it's still going to remain being red. Okay, I created this thing called, I wrote some code to develop boundary regions. All right, so this whole mess of code, basically what I've done, and this is based off of someone else's code that they wrote on Stack Exchange, okay? Basically what I've done is, what this code will do is it creates a grid of points, a fine grid of points, and for the grid it's going to do KNearest Neighbors for, say, k equal to 1, and then we draw a boundary. So this is, so if you just kind of squint and you look at the red and blue dots, this image is still the same exact red and blue dots, okay? Maybe just scaled a tiny bit differently, okay? And then here I created this grid of points, and so, you know, this took my computer, well, it didn't, actually my computer's kind of fast, so it wasn't too bad. But basically, we said, all right, for this dot right here, what is the one nearest neighbor? And it ends up here, right? And then we looked at, you know, for this dot here, what's the nearest neighbor? It's blue. And then so it's kind of like at this dot, this is the red one's closer, and over here the blue one's closer. And so we end up getting this boundary region between, for k equal to 1. And we say, all right, everything over here is red, everything over here will get classified as blue. So wherever your test case is, they will get classified as red over here when k equals 1 versus when being k equals when it's blue, okay? And so we can kind of see the influence of each of these points, right? Like this boundary here is created by these 2 points. This, these 2 points create a boundary here. These 2 points create this boundary. These 2 points create this boundary. These 2 points create this boundary. And then who creates, oh, these 2 points, this one and this one, are responsible for this boundary over here, okay? And so it's kind of like, if you draw a line that connects red and blue, you end up getting like a perpendicular line that goes through it. Red and blue, you get a perpendicular line. Red and blue, you get a perpendicular line. It's kind of interesting how this works, right? So this line right here is created by these 2 points. These 2 points create a boundary. And then I think these 2 points create this boundary here. And these right over there. Okay, so anyway, that's what we, k equals 1. At k equals 3, this is what ends up happening. All right, and so, you know, this dot ends up on the kind of wrong side, and this blue dot ends up in the, you know, wrong side. just imagine, like, I guess I saw like West Side Story not too long ago, and you know, it's like these streets are ruled by the sharks and these ones are ruled by the jets, and so I'm just imagining, like, I don't know. Okay, it's a great movie, by the way, the classic, and the remake is also quite a bit of fun. Okay, what was I saying? All right, anyway, red over here, blue over here, and so you know this, you know, what are you doing in our part of town? Okay, where are all of your other friends? So you know this is what happens. Okay, with k equal to 3, and as we increase k, the boundary, I don't know if smoother is the right word, but it's less influenced by any one individual point, right? So k equal to 1, each individual point kind of has its own like bit of influence, okay? But as your k increases, now it requires like the dots to work together, and this one dot doesn't have as much influence or things like that, okay? And so here we go, as k, the number k gets larger. Okay, that's k equal to 7. I guess I'll give you your second view quiz answer, which is the letter C. C as in cat. Okay, so here is more data, a little bit more of a mess. And now you're given the task, draw a boundary between the red and the blue, okay? How do you do something like this? How do you say, all right, which areas are red and which areas are blue? And so we're kind of like down here, we feel like, okay, we can draw a line right here, right? Like this feels like this is where red and blue influence, and I don't quite know. Up here it's a little bit like, do I go here? Do I include these? Okay. So if you do k equal to 1, so again, here's the data, and the next, this is the exact same dots. We've just put a grid over it, and I just didn't put any more dots over here because you know, these would all be red and these would all be blue, I guess. Oops. Okay. So at k equal to 1, you can see the influence each one dot has, right? So you end up getting these little like enclaves and exclaves of, what's the difference between an exclave and an enclave? I don't know. It's like you have all of these things in Russia, in Europe, right? Like Russia has that little bit right next to Lithuania, and then like Gibraltar, that's like owned by Britain, right? Even though it's like at the end of Spain. And you guys don't know what I'm talking about? We're gonna have a geography lesson today, all right? Maps.google. Can we just go over to Gibraltar, United Kingdom? Oh, that's actually the United Kingdom. No, we want, so I think, British Overseas Territory, yeah. Poor Spain. This little bit right here, this little bit in red. Britain said, we're still keeping it. This strategically very important point that controls the in and out of the Mediterranean. Just so you know, Spain, we are Britain. We own this piece, right? Yeah, okay. And then there's a bunch of these like weird things, right? So over here, this is like Russia. This is actually Russia. Kaliningrad. Oh no, Kaliningrad. Okay, anyway. All these exclaves and stuff. Okay, let's look up enclave versus exclave. Let's see. An enclave is a territory that is completely surrounded by the territory of one other state. An exclave is a part of a state that is geographically separated from the main part by the territory of one or more states. Okay. You want me to click this? So, like, not Lesotho. What is it called? Eswatini? Right? Guys. Oh, no. It's, okay. What are we doing here? Okay, so Lesotho is completely surrounded by, this would be an enclave.
Yes.
Oh, I guess Swaziland and Eswatini. I guess, it does have a border with Mozambique. Okay.
No, it's like
So that, okay, well, this is not helpful when you don't label these things. All right.
A2 is
Okay. This would be an exclave. All right, well, anyway. Okay, so anyway, you get that when you have k equal to 1, right? You get these exclaves over here, and you know, each individual dot creates its own little sphere of influence. Okay. And so with k equal to 3, now you need at least like two friends together to kind of create this. Okay, otherwise, you know, this one lone person doesn't create anything. It's kind of funny right here. These two blue dots create their own little exclave, you know, sphere of influence right here, but it's a little bit funny there. So with k equal, so here's k equal to 1, k equal to 3, and again, as we increase our k, you know, we're less influenced by these kind of dots that are quite out there, right? And so I'll just kind of keep ramping up the k's, and you can see the border. So here's 1, as I'm going up, the border between the things get kind of a lot more smooth, right? So here, k equal to 31. Now we're like kind of just drawing a line straight up, right down up the middle. Like this side is red and this side is blue. It's simple, right? K equal to 21. Pretty much not a huge difference between these two, and I'm not 100% sure. Like, apparently, if you go to this dot and you say, what are the 21 closest neighbors, which is, you know, quite a bit of things to figure out, they'll say, okay, these are you know, red and blue and stuff, right? Here, k equal to 15, k equal to 9, k equal to 7, and so at all of these things, you know, I'd say by this point, the border is fairly smooth, okay? And again, for smaller values of k, the border gets a lot more wonky and harder to distinguish. Okay, so anyway, that's basically it. K-nearest neighbors. It's a simple enough algorithm, and it's sometimes you can just kind of use it to get a sense of where your borders and regions might lie. Again, it is computationally expensive, especially if you have a very large data set, because you got to figure out the distance to every single other data point, which is undesirable. And the other severe limitation is that all of your variables pretty much have to be numeric or made into something where you can measure numeric distances. So if you have categorical variables, you have to be able to say, okay, well, what is the distance? You have to be able to turn it into some kind of distance. You know, what's the distance between a red car and a black car, or a white car and a silver car? And you have to have some way to say, okay, well, the distance is this and the distance is that. And if you're not able to turn those kind of categorical differences into numeric distances, then you can't use this, because it's all based on this idea of distance. Okay, and that's it for today. So just a short lecture on KNearest Neighbors with a touch of geography here. And let me give you your last view quiz. The letter D as in dog. D as in dog is your last view quiz answer. All right, have a good weekend. We will see you on Monday.